Hello everyone, welcome back to my channel. Today we are going to talk about data science and its application. Now let us see the concepts. Continuous distribution, the normal distribution, properties of normal distribution, the central limit theorem, sampling distribution and standard error, hypothesis testing and p-values, confidence intervals, continuous distribution in data science, limitations and assumptions, conclusion and key takeaways. Now let us see continuous distribution. Exploring the fundamental concepts, continuous distribution are powerful statistical models that describe the behavior of variables that can take on any value within a range. The introductory section provides an overview of the key concepts and their importance in data analysis and decision making. Now let us talk about the normal distribution. Definition. The normal distribution, also known as the Gaussian distribution, is a fundamental continuous probability distribution widely used in statistics and data science. Bell-shaped curve. The normal distribution is categorized by a symmetrical bell-shaped curve with the majority of the data concentrated around the mean. Importance. The normal distribution is crucial for understanding statistical inference, hypothesis testing, and modeling many real-world phenomena. Properties of the normal distribution. Symmetry. The normal distribution is perfectly symmetric around the mean with equal probabilities on both sides. Mean, median, and mode. The normal distribution, the mean, median, and mode are all equal, located at the center of the curve. Standard deviation. The standard deviation determines the spread of the distribution and the probability of data falling within certain ranges. Empirical rule. The empirical rule states that approximately 68%, 95%, and 99.7% of the data falls within 1, 2, and 3 standard deviations of the mean, respectively. Now let us see the central limit theorem, sampling, significance, and independence. Now let us see sampling. The central limit theorem states that as the sample size increases, the sampling distribution of the sample mean approaches a normal distribution. Significance. The central limit theorem is a powerful result that underpins many statistical inference techniques, such as hypothesis testing and confidence intervals. Independence. This holds true regardless of the underlying distribution of the population, as long as the samples are independent and randomly drawn. Now let us talk about sampling distributions and standard error. Sampling distributions. Sampling distribution describes the behavior of statistics such as the sample mean, calculated from random samples drawn from a population. Standard error. The standard error measures the variability of a statistic such as the sample mean and is used to quantify the uncertainty in the estimate. Importance. Sampling distributions and standard error are crucial for making inferences about population parameters and conducting hypothesis testing. Now let us see hypothesis testing and p-values. There are four types: null hypothesis, alternative hypothesis, p-values, and decision. Now let us see one by one. Null hypothesis. The null hypothesis represents the default or status quo which is assumed to be true until proven otherwise. Alternative hypothesis. The alternative hypothesis is the claim of statements that the researcher is trying to provide evidence for. P-value. The p-value is the probability of obtaining the observed or more extreme test statistic given that the null hypothesis is true. Decision. The p-value is compared to the significance level to determine whether to reject or fail to reject the null hypothesis. Now let us see confidence intervals, population parameter, sample statistic, confidence level. Population parameter. A confidence interval provides a range of plausible values for an unknown population parameter. Sample statistic. The confidence interval is calculated based on a sample statistic such as the sample mean. Confidence level. The confidence level represents the probability that the true parameter falls within the calculated interval. Now let us see continuous distributions in data science. Modeling real-world phenomena. Continuous distributions, such as the normal distribution, are used to model a wide range of real-world phenomena, from heights and weights to financial returns. Statistical inference. These distributions form the foundation for statistical inference techniques, allowing researchers to make informed decisions and draw meaningful conclusions from data. Predictive analytics. Continuous distributions are crucial for building predictive models, forecasting future outcomes, and quantifying uncertainty in data science applications. Now let us see limitations and assumptions. Assumptions. Continuous distributions such as the normal distribution rely on certain assumptions such as independence, normality, and homogeneity of variance. Robustness. While these assumptions are important, many statistical methods are relatively robust to minor violations, allowing for wider applicability. Alternatives. When the assumptions are severely violated, alternative distributions or non-parametric methods may be more appropriate for the analysis. Now let us see the conclusion and key takeaways. Continuous distributions, particularly the normal distributions, are fundamental concepts in statistics and data science. They provide a powerful framework for modeling, inference, and decision making with wide-ranging application in various fields. Understanding their properties, assumptions, and limitations is crucial for effective data analysis and drawing reliable conclusions. Thank you for watching the video. Please do like, share, and subscribe my channel.